Hello, this is my second video for project 3 for fluid mechanics. As you can, in my last video, I did viscous laminar, and so now I'm going to show you how I did my viscous turbulent flow around a cylinder. So I'm just going to bring in a new system. I'm going to call it video example turbulent. And as I said in the previous video, the geometry for all three of the cases is the same. So I'm just going to import geometry and use the cylinder wall that I've used for all of them. So now I'm going to go into Mesh and I'm going to click Edit. Okay, so now that I'm in the CFD base, this is a very similar mesh to the previous video, but I'm just going to go through it again. I'm going to first name all of my edges. So the top and bottom is just going to be symmetry. We don't want them to be considered walls or anything because then otherwise they'll mess with the flow at the edges. Our area is pretty big, but just in case, we're gonna, make sure that they're not walls. My right side is gonna be a pressure outlet, and my left side is gonna be my velocity inlet. And in the center, we've got our cylinder, and that's gonna be called cylinder wall. Okay, so now that I've named all of my edges, I'm going to go to Mesh. I'm going to select Method, select the surface, and we're going to use a triangular mesh to start out with. Going to click Generate, and now we have a very basic mesh. And now I'm going to insert sizing, and it's going to be around the edge of the circle. I'm going to make sure that I have number of divisions, and I'm going to be using 500. Yep, that looks right. And I'm going to make sure that my behavior is hard and click Generate. Okay, so now that we've generated our mesh with the additional edge sizing, I'm going to add inflation, select the base, and I'm going to make sure that our boundary is our circle. So here we're going to do first layer thickness. It's going to be 1 meter, and our maximum layer is 150. Right, and click generate. Okay, so that mesh was generated in, and you can see the inflation making a much more defined and accurate mesh around the cylinder. And so I'm just gonna make sure that my element sizes around that inflation are the right size. So I'm gonna do 0.6 and I'll hit generate. Okay, so now our mesh is far more defined. And I believe that's it for the mesh creation. So I'm just gonna go and update our mesh. And now I'm gonna get into the main CFD. I'm gonna select double precision and I'm gonna use 4 processors. Okay, so now that our mesh has loaded in, we've got pressure-based, steady, and planar for our general settings. So that seems to be right. In models, I'm gonna select a different model that just worked better for turbulent flow, which is the K epsilon model. And under K epsilon model, I'm going to do realized. For near wall treatment, I'm going to do enhanced wall treatment so that around the cylinder, it has more accurate calculations. I'm going to choose curvature correction. And for the TDR, um, which I'm pretty sure just means um, I forgot what it means. But for that, I put zero point 0.2. And that's it for the model, I believe. So I'm just going to click OK. And so now in materials, I'm going to be using air, and I'm just going to make sure that the um, density and viscosity look okay. Yep. Okay. And just to double check that the calculation is going to be using that air. Yep. And so now in boundary conditions, I'm going to make sure that my velocity inlet. So for our velocity inlet, I'm going to do a magnitude of 7.3 meters per second. And because of the model I chose, it gives me a new turbulence option. Um, Here, I'm going to leave these the same. So turbulent intensity is 5% and our viscosity ratio is 10. I'm going to close that. And I believe that's the only change that we need to make to our boundary conditions. But I'm just going to double check that all of our other conditions look correct. Yep, here we have, yep, 5% and 10. And for our cylinder wall, it should be stationary and it should be no slip. Okay, well, that looks good. And so I can go on to reference value, make sure that I'm computing from the velocity inlet. Everything looks correct. Make sure I select surface body and move on to methods. So here, the solution method that I used was simple C. Um, I know a lot of other people did simple and some other ones, but I just found that simple C worked for turbulent flow. For gradient, I'm doing green gauze node based. For pressure, second order is correct. Momentum, second order. And for turbulent, they're both first order. And I'm going to go into report definitions, create a new force report where I'm going to report the the drag coefficient. And that's going to be on the cylinder wall. Click OK. And I'm now ready to initialize, but first I'm going to make sure that I'm running 30 iterations just to make sure that everything's good. And now I'm going to click calculate. And I'm going to use 500 iterations. Okay, so now that our calculations have completed, I'm just going to go back to our report definitions, drag coefficients, and I'm going to click compute. And yep, that drag coefficient looks good for our to match our theoretical understanding. Additionally, the all of the values for density and viscosity for air and the velocity that it's moving, they all make a Reynolds number of roughly 500,000, which just makes the edge of turbulent flow without making you know, any vortexes or anything that would make it unsteady. Um, so now I'm just going to go to plots and I'm going to go XY plot. I'm going to create two of them. The first one is going to be pressure coefficient. And this is going to be along the cylinder wall. And so here you can see the bottom line matches up with the theoretical for the pressure coefficient along the cylinder wall from 0 degrees to 360. At least I believe the lower wall is 0 to 180, I believe. And so that is what should be correct. And so I'm going to go and create another plot. And this is going to be velocity along the wall, velocity magnitude, and plot that. And again, it should be 0, like the laminar case. That just meets with the theoretical values. So that's it for the CFD base. And now on to results. And so now I am in CFD post. I'm going to create a few contours. My first one is going to be a pressure contour. I'm going to use symmetry 1, making sure we have pressure, and I'm going to use 100 contours. And so here you can see the pressure distribution along with the flow. You can tell that there are two spots of low pressure in the wake of the cylinder. And you'll see more clearly with the velocity contour how turbulent the flow is. So I'm going to select symmetry, velocity U, 100 contours. And so here you can see the velocity contour. Um, I tried to get a smaller turbulence wake, but this was the best that I could get with keeping air constant, those values for air constant. Um, I'm also going to do this velocity streamline. Starting from the velocity inlet, I'm going to use 5,000 points. And so here you can see the streamlines. It's it definitely rejoins at the end, and there is a turbulent wake. Okay, and that's it.